Hello everybody, welcome back. Today's lesson, 113, covers direct variation and inverse variation. Now fortunately we talked a lot about this in pre-algebra. Hopefully it won't be too new and too full of new information. So I know your brains are about to explode, but hang in there, we're almost done. Direct variation problems are ones like, if you buy a movie, a DVD, and they're $20 a piece, and if you buy 5 of them, you've spent $100. Or if you mow a lawn, and you charge $20 times 3 yards, you've made $60. Babysitting hourly, or maybe there are in a classroom for every one girl, there are 2 boys, okay? So there's a constant that doesn't change, like the amount that you charge for cutting the lawn, or the babysitting charge, or the price of the CD. So those are direct variation. And so we'll talk about those first. And they may say that they're directly proportional. Okay, so I really want you to read through this lesson. I think that it'll help you with things that I might not hit so hard. But they'll always be in the form of y equals kx, all right? The constant being the thing that doesn't change, okay? Like the rate of your driving. Maybe you're driving down the freeway at 70 miles an hour, so that rate stays the same. If you've gone 3 hours at that rate, you'll go 210 miles, right? So distance equals rate times time, where the rate is unchanging. Okay, I know you can change by going faster or slower. We're saying at a constant speed, okay? All right, so as I said, it could say varies directly, it could say directly proportional, or is proportional to, something like that. So do read through these and make sure that you know the different ways that they're set up. So let's start on page 475 with the first example. Now, this one says that the mass of a substance varies directly as the volume. So when I hear that varies directly, I know my brain's going to signal that that's a, y equals kx. So in this case, I'm going to write mass, okay, varies directly as the volume. Okay, so my constant times the volume. So what you're going to do then is plug in values that they give you, find the constant, and then use that constant with new values, okay? So let's read through this. The mass of the substance varies directly as the volume. So you see I've set it up. Mass equals constant times volume. If the mass of 2 liters of the substance is 10 kilograms, okay, so 10 kilograms is my mass, right? The constant I'm looking for, and the volume is 2 liters. Okay, so you see what I've done. I put the 10 for the mass, the 2 for the volume, and now let me find out what the constant is under these conditions. So obviously I would divide by 2 on both sides and get a constant of 5. All right, now continuing on, it says then, what will the volume of 35 kilograms of the substance? Okay, what will be the volume of 35 kilograms of the substance? So I'm now going to plug in, right, for the mass, okay, 35, okay, equals the constant times the volume, all right? So I would divide by 5 and get that the volume would be 7. And so volume in this case is liters, okay? So that's where I'm going to end up. All right, let's do another one. I think more practice will help us. Okay, the next example. The distance traversed by a car traveling at a constant speed is directly proportional to the time spent traveling. Okay, so we're very familiar with this one. Distance is rate times time, okay, or that constant is my rate. So If the car goes 75 kilometers, okay, that would be my distance. Okay, the constant or the rate that I'm looking for in 5 hours. Okay, so I hope you see what I'm doing, plugging in the values. All right, so my rate, or my constant in this case, dividing by 5 is 15, and I'm dealing in kilometers per hour. Okay, then it says, how far will it go in 7 hours? So I've found the constant under these conditions. Now I'm going to plug in the 7 hours, okay? So I'm looking for the distance with the rate of 15, the time of 7. And so in this case, I would have 105, and this problem is dealing with kilometers, okay? Now some people are going to write all these units, you know me, I'm always shortcutting things. But if I read through the problem, I know what I'm dealing with. All right, let's do the third example. Under certain conditions, the pressure of a gas varies directly as the temperature. Okay, so the pressure varies directly as the temperature. Okay, pressure, constant, temperature. So when the pressure is 800 pascals, so I'm going to plug in 800 here, the temperature is 400. And here I'm dealing with kelvins, okay? So I'm going to divide both sides by 400 to find my constant. Okay, so my constant is 2, right? So now I'm going to plug in pressure equals 2 times the temperature, all right? And so it says, what is the temperature? That's what I'm looking for when the pressure is 400. Okay, so 400 equals 2 times the temp. So obviously the temperature would be 200, and I'm dealing with K, so I'm going to put that in my answer. All right? All right, so now hopefully you've got direct variation. You know what to do there. And I do want to remind you that with direct variation, you will go through the origin if you're plotting these, and you would have a line, right? The graph would be linear, okay? Just food for thought there. All right, now let's erase and let's go to inverse variation. All right. And these, of course, are going to be problems where as one variable increases, the other decreases. Okay, so these will not be linear. You're going to have something like this, a line, you know, a curve, right? Okay, so let's remember then also that this will be in the form of y equals k over x. Okay, so again, maybe if 10 workers take 6 hours to do something, then 5 workers would take how many hours? So as one variable goes down, the other goes up. Okay, so if 10 workers took 6 hours, then 5 workers would take 12 hours. Okay, those constants are going to be the same. We're going to be multiplying y times x, and that should always be the same with inverse variation problems. Okay, that y times x will always be the same number for each different problem. All right, so let's do an example here. So, and again, please read through and take a look at the presentation of the lesson and then go to the problems, okay? All right, so 113.4. Under certain conditions, the pressure of a perfect gas varies inversely as the volume. So when I hear that varies inversely, I know that I'm going to write it like this. Okay? So pressure varies inversely as volume. All right, let's plug in numbers. So when the pressure of a quantity of a gas is 7 pascals, let me put 7 right there, then in that case, the volume is 75 liters. Okay, So then it's asking what will the volume be if the pressure is increased to 15? Well, first of all, I'm going to have to find this constant. So think about it. It's like I'm cross multiplying, okay? So constant then will be 75 times 7, which apparently is 525, okay? Now, I'll plug that in, okay? So I don't want to run out of room. So I'm going to plug in the 525. Okay, and the question is, what will the volume be? What would be the volume if the pressure is increased to 15? All right, so pressure increased to 15 equals 525, the volume, all right? So again, it's like I'm cross multiplying, right? So V times 15 is 525. So I'm going to be dividing both sides by 15 and get a volume of, apparently this is 35, and I'm dealing with liters in my volume, so that's what I'll put for this answer. All right, let's look at the last example. Okay, this one says, to travel a fixed distance, the rate is inversely proportional to the time required. Okay, so rate inversely proportional to time. So when the rate is 60 kilometers per hour, okay, so 60, and look for the constant. When the rate is 60, the time required is 4. Okay, so in this condition then, the K would be 240. Okay, everyone see that, I hope? All right, so now let's go and put rate is 240 divided by time, because I found the constant under those conditions. So then the question continues, what would be the time required for the same distance if the rate were increased to 80 kilometers per hour? Okay, so we're going to say rate is 80. We know the K is 240, and we're looking for the time. Okay, so again, it's like we're cross multiplying. So 80T is 240, and so T would be 3, and we're dealing with hours, right? And again, does that make sense? The rate here was 60, and it was 4 hours. We increased the rate, but we decreased the time. So it did work, being inversely proportional. All right, I hope these examples made sense. I want you to try practice A, B, and C. So stop the video and then come back and check those, and you can proceed to the lesson. Okie dokie. So for A, the mass varied directly as the volume. Okay, the mass was 30 and the volume was 6 liters. So I found the constant to be 5. So then I plugged in, because it then asked what is the volume of 65 kilograms of the substance. So I used the constant and found the volume to be 13 liters. All right, for B, the pressure varied directly as the temperature. All right, when the pressure is 1200 pascals, the temperature is 300 degrees Kelvin. Okay, so I found my K, my constant, to be 4, finding that algebraically. Okay, then I plugged in the pressure, because it asked then what is the temperature when the pressure is 300 pascals. Okay, so I used the constant and algebraically found the temperature to be 75 K. Now that's not constant, that's the Kelvin. I should make that a nice big K, right? Okay. All right, and then C, the pressure varied inversely as the volume. Okay, so I set it up like this. It said that the pressure is 9 pascals, the volume is 100. So algebraically, my K was 900. Okay, then I rewrote the problem under the conditions of the pressure increased to 20, right? The constant over the volume. So algebraically then, the volume was 45 liters. Okay, so check RenWeb, see what your lesson is, get started, and have a wonderful afternoon. God bless you.